Hello. We learned the method of separation for solving differential equations of order 1. And we were very happy with it. It's a very popular method, probably one of the most popular methods. However, not every differential equation of order 1 is separable. We saw an example like that before. This is a very nice looking differential equation, very simple, and yet it's not separable, so as of now, we don't know how to solve it. And we therefore need another approach or another type of a differential equation to explore. And in fact, there are many types for which we know approaches, how to solve them. But most of them are very narrowly specialized and beyond the scope of this course. However, with one exception. Linear differential equations. That's a very important group and also a very nice behaving group. So that's a good combination, something which is useful and nice. Here we will focus on the first order differential equations. So first order linear differential equations are given by a formula which is on the second row on the left. That's the typical shape. Let's check our example. Okay, I want to see all the y's on the left. This shouldn't be a problem. And I want to see plus there. So I'm going to write it like that. So all the unknown functions on the left. Here is just the x, the working variable. And when I compare it, I can see that this is actually ax, and this is actually bx. So this really fits nicely. Now for the linear differential equations, there is an interesting procedure which we will see today in a simplified version. And later on we will generalize it because we will have linear equations, linear differential equations as a major topic coming up soon. So what's the procedure? Well, actually it comes in two stages. And in the first stage we will solve the associated homogeneous equation. That's the usual trick with linear equations. So we look at the homogeneous version, which is y prime minus y is equal to 0. Now the beauty is that this homogeneous version can be always solved by separation. Let's see. What's the variable x? Actually, this is an exponential growth, so we should be able to guess the solution right away, but let's go through it. Okay, let's do separation. There are two possible options here. One of them is that y is not 0. If y is not 0, we can divide, and we get integral dy over y is equal to integral 1 times dx. And now we integrate. Logarithm y in absolute value is x plus c. And now we use the usual trick. We raise both sides to the exponential, and then we get rid of the absolute value using the plus minus trick. So y is equal to plus or minus e to c times e to x. And now we introduce a new constant for this group, and we get yt or yx is equal to d times e to x. X belonging, well, there is no restriction anywhere, so x belonging to real numbers. Now that's the solution of my homogeneous version. So let me put it here, yh, let me emphasize it. To complete the solution, we should recall that when y is equal to 0, this gives me a stationary solution. And we can incorporate it into this formula by taking d equal to 0. So we saw it before. This is one of the, let's say, most frequently appearing types of separation. And we are happy with it. That was nice and smooth. Okay, that was the easy part. Now comes the fun part. This is a very nice solution, but it actually solves a different differential equation than we want. We want to solve this one. And here comes the idea. I decide to look for a solution that has the same form, but I decide to put a function instead of constant d. So in a way, this is a guess. I'm guessing that it's possible to find a specific function dx, so that if I put it here, then this becomes a solution to my original problem. And this is called variation. Why? Well, because I take a constant and I start varying it. I start changing it. It now changes with time or with the independent variable. What's the justification? That's a very good question. What gives me the reason to believe that actually I can find a solution of this form? And actually, I don't have a good story coming with it. Unfortunately, I don't know it, and I wasn't able to find any justification why something like this should work. Our forefathers, they didn't have computers. They had to use their brains instead. So they were trying all kinds of different approaches, even crazy ones, because they were desperate. They really needed to solve differential equations, and they came up with this. And it turns out that it works, as you will see. So that's the variation. I cannot explain why they came up with it, but you will see why it works, and I will justify it. Let's go with it. Okay, what's the setup? I say, okay, I'm looking for a function dx so that this formula becomes a solution. How do I find this dx? The answer is, well, I will simply try it. I will take my guess for the solution. This is the shape or pattern, if you want, for the solution. And I put it into my differential equation, the given one, the complete equation, and see what happens. So on the left, I should take derivative. I take derivative. I don't know d, but I don't care because I'm good. I passed my calculus course. I can differentiate product. So here we go. I differentiate the first part, and I differentiate the second part. That's it. That's actually my favorite derivative, or the second favorite. My favorite is derivative of 0. Okay, here we go. Equality, then there is x, and then there is y. And I get an equation. Now at the first sight, this is not really any better than what I had before, because I have an unknown function, dx, and I have an equation with dx and also with the derivative, so that's a differential equation. However, at the second sight, I can notice this, the miracle of cancelling, which totally transforms the situation, because now my equation looks like that, which means that the d prime is just x e to negative x. That's a very nice equation. I can solve it, I just integrate. Here we go. dx is equal to integral x e to negative x dx, which is integration by parts. Here we go. I'm going to differentiate the x part to get rid of it. So I have to integrate whichever part is left, which is the exponential. So I integrate first, that's the rule. And by integrating, it becomes minus x e to negative x. Now, minus integral of this term, but with x differentiated. So minus and minus becomes plus. I differentiate, so it disappears, and there is just e to negative x dx, which is, now we should get the answer, let's see, minus x e to negative x, and I integrate, and I get minus e to negative x plus c. So that's the function dx. If we did make any mistake, then this function dx that we just calculated should turn my pattern into a solution. Let's see. What's yx? Yx is dx times e to x. Minus x e to negative x minus e to negative x plus c times e to x. We multiply out and we get minus x minus 1 plus c e to x. And this is true for x belonging to R, because there is no restriction, no. So here we go. I claim that this function yx is actually a general solution of the given equation. How do I know? Well, first of all, I can see a parameter here, a constant that I can choose, which suggests that this is not just one solution, it's infinitely many of them, which is wonderful. And I can simply take this formula, substitute into my equation, and it turns out that it works. It's really satisfied on real numbers. So this is a solution. It's harder to show that there are no other solutions, but it can be done. So this is really a general solution. And this procedure, something that we call variation, really works. It's a very nice algorithm. Before we move on, let's make a few remarks. Some people, when they come to this part, when they start learning about variation, they already know the theory for linear differential equations. And if you know the theory, you can make some shortcuts, sometimes if you get lucky, or perhaps try to move it in a slightly different way. Here is a shortcut possibility. So we return to this homogeneous equation. Y prime minus y is equal to 0. Now, people who know linear differential equations, they know how to solve these equations, assuming that the coefficient here is a constant, which is true. This is -1 here as a coefficient. And the procedure goes like that. I pass to a characteristic polynomial. I solve it. And based on the characteristic polynomial, I create the homogeneous solution. So that's definitely a shortcut compared to the separation. However, not always the coefficients are actually constants. And if they are not constant, you do have to follow through with this separation part. So this is the general approach, going through the separation with the homogeneous equation. And this is the shortcut version if you get lucky and if you know it. The second interesting alternative concerns the general shape of a solution. For linear differential equations, we know that the general solution can be obtained by taking some particular solution and a homogeneous solution. Now, the homogeneous solution we already have here. We determined it a short while ago. Particular solution is just one particular solution. We can do it like that. We follow the variation way, just like we did before. And there are the steps that follow, and they get us all the way here. And now we can do something which is a crime generally. We can integrate without putting a integration constant. So for dx, we take just some antiderivative. Now, if I wrote this in my calculus course, I would have to deduce points to myself, because this is wrong in calculus. But here we have a special permit to actually not write plus c, so let's enjoy it. Let's use this opportunity. I just take a specific function for d, and therefore I get a particular solution, which is, well, exactly as we did before, just there is this c part missing. So there will be minus x minus 1 after we multiply this through by e to x. And then, according to this formula, the general solution will be yx is equal to the particular solution plus the general solution, which we copy from there. And when we look at it, when we compare them, it's the same formula. So these are two ways to get to the same target, to the same solution. And it's up to you whichever you prefer. I actually slightly prefer this one because it's more in tune with the general theory. It's more structural. It's based on some structural theorems, which I really enjoy. So I prefer this way. And also, well, I don't have to put plus c when I integrate. This is such a special occasion. So I'm enjoying it. Yeah, but this is a good way as well. So it's up to you. Anyway, that's one specific example. And our good question is, will it work for other equations? That's a very good question. Yeah, let's have a look. I captured here the major steps or the salient features of the variation as we saw it in our previous example. And now I will try to repeat the same steps, but for a general linear differential equation of order 1. And I will keep track of all the assumptions that we have to make in order for the variation to work. Now, the first assumption, of course, is that our equation is linear of this form, but that's an obvious assumption. The second assumption that comes in is less obvious, but still easy. We are looking for solutions on a certain interval. And of course, on this interval, this equation has to make sense. So we definitely want the coefficients a and b to exist, so to be defined on some interval I. That's our first assumption. And then we can start solving. So here we go, the first step. We looked at the homogeneous version, which in this case looks like this. Y prime plus axy is equal to 0. And I claimed that this can always be solved by separation. Let's see. Well, dy over dx is equal to negative axy. So far so good. Now we can rearrange it a little bit. We get integral dy over y is equal to integral minus ax dx. And this is under the assumption that y is not equal to 0. Now we integrate. Logarithm of y in absolute value is, well, this is where it gets interesting. I'm integrating function minus ax. I can pull the minus out. So my question is, how about integral of ax? Now, there is a very natural requirement for the integral to exist, which is continuity. We know it from calculus. Every continuous function can be integrated. So, now this is a major assumption. These were sort of obvious. Ax should be continuous on interval I, and we can, let's say, use capital Ax for the antiderivative on interval I. And therefore, if I take into account the sign here, we get minus capital Ax plus c. That would be the outcome of the integration. And again, as before, we solve for y. So we apply exponential to each side. We get rid of the absolute value in the usual way. And we get y is equal to plus minus e to c e to negative ax, capital Ax. And finally, the usual trick, we call this plus minus e to c by, let's say, d. And we get the homogeneous solution, yhx, which is d times e to negative ax. And x belongs to the interval I. Everything now happens on the interval I. And as before, just to complete a picture, we comment that when d is equal to 0, this includes the stationary solution, yx is equal to 0. So we have a complete picture, which fits in well with our previous attempt. Let's see. Here, ax, when we compare it, ax used to be negative 1. The antiderivative of negative 1, well, we have a choice, but just to make it simple, is negative x. So I put negative x for ax, and I get e to x. E to x, that fits. So this general pattern really fits with our specific example. So far, so good. Now, let's have a look at the second step. And that's where things get interesting. Now we take this homogeneous solution, and we use the variation idea, which is really weird, but it seems to work, and change a constant into a function. Yx, okay, I will go the traditional way, assuming that we don't know any linear theory. So I will simply look for a solution in the following shape or pattern. dx, that's an unknown function, times e to negative ax. That's my guess, in a way. But it's a very educated guess. Let's see, can I find function dx so that this becomes a solution? Well, we take this, my guess for the solution, and substitute it into the whole given equation. So we start by taking the derivative. Let's see. By the product rule, we differentiate the function d and multiply it by the second function. Plus, we keep the first function and we differentiate the second one. So we differentiate the exponential, that's the outer function, and multiply it by the chain rule by the derivative of the function which is inside, which is minus capital Ax. This is differentiated. And this all is y prime, just to keep track of things. Y prime is done, plus axy. Okay, no problem here. What is y? This is y. And this should be bx. So far, so good. Now, do we see any miracle of cancelling happening? And the answer is not yet, but that's because we didn't figure out this bracket yet. Derivative of minus ax. What is it? Well, this is minus, and the derivative of capital A is lowercase a. This is minus ax. And now we look at it, and we can see a certain expression here, and we can see the same expression here, just with the opposite sign. So this part and this part, they do cancel. Miracle of cancelling. It's actually guaranteed. Is it still a miracle if it's guaranteed? That's a good philosophical question, which I'm not going to go into. But I'm really happy that we have this cancelling, because otherwise the procedure would stop. We couldn't go on. Let's have a look at it. D prime x e to negative ax is equal to, and everything's gone, and there is just bx. The original right-hand side of the equation. And this is a very nice pattern. You make your guess, which is here, by variation. And then you get the equation just by putting differentiation sign here, this little apostrophe, and you put bx on the other side, which you can see right from the equation. So that's very nice. Now, does it fit with our previous example? Well, let's see. After we substituted and cancelled, we got d prime e to x, which is exactly the right form, is equal to x, which is the right-hand side. It perfectly fits. So again, this works in general. And now we have to move on. We didn't really need any assumptions here. Essentially, the only assumption was that d will be a differentiable function. But we will see that it works. Okay, here we go. D prime x is equal to bx e to ax. And therefore, dx is equal to integral bx e to ax dx. And now we have to start thinking, okay, I want this integral to exist. And as usual, my preferred way how to force it to exist is to make this integrand function continuous. Now, ax is a continuous function because it's an antiderivative, so automatically it must be continuous. I compose it with exponential, so this whole part is continuous, and therefore I just need to worry about b. That's my another assumption. I want bx to be continuous on I, and then I can use, let's say, capital Bx as an antiderivative, but of what? Of little bx e to capital Ax on I. So that's my probably last assumption. Let's see. Does it fit? Yeah, I copied it correctly. And therefore, I can write here that the dx is this antiderivative plus integration constant c. And finally, we can finish our work. We take this dx and substitute it into our pattern, into our guess. And we get yx is equal to bx plus c times e to negative ax. X belonging to the interval I. And that's a general solution. Again, one can prove it by substituting into the given equation, which shows that this is a solution, and the fact that it captures all possible solutions, that takes more work, it can be done. So the variation approach, which may look weird at the first sight, but it works, and it's reasonably simple if we get lucky. This variation procedure actually works, assuming that we have continuity of the coefficients. These are relatively mild assumptions. I mean, if those functions are not continuous, then we usually are in such a big trouble that we don't have to worry about variation. We worry about more important things then. So in reasonable applications, A and B will be continuous. So that's wonderful, but these are just theoretical assumptions. In actual calculations, when it comes to integration, well, you know that sometimes theory says, well, there is an antiderivative, but we actually cannot find it. Perhaps even theoretically. There are those known functions which are continuous, but you cannot express the antiderivative by a formula. Those functions are known from the calculus course. Or perhaps they are expressible as a formula, but you don't know how to find them, because integration is a tricky business. Well, if you went for an exam in calculus, you know what I'm talking about. So this may theoretically exist, but there may be some troubles in actual calculations. But it's another story. This is a very, very nice method. Essentially, when I see a linear differential equation, well, it actually may be sometimes separable, and then I prefer separation right away. But if it's not separable, I try to approach it in this way. And then everything depends on those integrals. If I can handle them, I get a solution. Very nice. This is actually a proof of the following theorem. Let's have a look at it. This theorem confirms that if A and B are continuous, then we can actually find a solution in a certain shape, which corresponds to roughly this part combined with this part. And if we use the notation capital B, then we get a solution of exactly this shape. So this is really just a summary of the procedure that we did here and confirmation that from mathematical point of view, everything is perfect. So that's the variation. Some comments. First of all, we just extended our powers when it comes to solving differential equations. Our repertoire is now wider because there are new differential equations that we can solve. We didn't know how to solve them before, now we know, which is wonderful. Second, this idea of variation, weird but nice working, now we know it, can be actually extended. It can be generalized to other types of differential equations. Namely, we will see soon that when you have higher order differential equations, you can still solve them using variation. The same two steps, just things will be somewhat different for higher order equations. There will be some restrictions then. We only allow constant coefficients then, but that's another story. We will see it soon. We can also use variation to solve systems of differential equations. So this is a very, very powerful idea. The third comment. There is something which is called the integrating factor method. And sometimes people learn it in their calculus courses or in their differential equations courses. At the first sight, this integrating factor is a completely different procedure. But when you look at the formulas which are used there, you will actually see something like that. You will see something like that. In fact, the integrating factor is exactly the same thing as variation when it comes to equations of this form. It's the same calculations, the same procedure, it's just dressed up in a different way. Or the path which takes you to these formulas is different. And that's why I didn't talk about it, and I will not talk about it in this course, because for us, these two procedures, variation, integrating factor, they are just the same. And I prefer the variation point of view. To me, it's more straightforward. For the integrating factor method, you would have to memorize some formulas, and I hate memorizing formulas. I prefer to understand procedures. This difference of point of view becomes important when you try generalizing these methods, because the variation can be generalized in one direction and the integrating factor method can be generalized in a slightly different direction. So once you start looking at different types of equations, more involved equations, then you see the difference. But in this course we will not see it. So I will stick with the variation for the course. That was the third remark, and I guess that's about it. So let me return to the second remark, the generalization of variation. Now, if we want to generalize this method to other types of equations, we have to understand it well. In particular, we will focus on this miracle of cancelling. Where is it hidden? Which part of this setup actually made this cancelling possible? And one might think that the exponential is to blame, or to be grateful to, that exponential made it for us. But in fact, it turns out that this is not true. There is a more general procedure in place here working for us, and it's important to see it. So let's make another attempt at our solution, this variation step, But this time, I'm going to hide the specific shape of the homogeneous solution. Let me look at it this way. I solved my homogeneous equation, and this solution came with the form c times some function, ux. Now, what is the function ux? Well, it solves the homogeneous equation, the associated homogeneous equation. That's the only thing I need to know about ux. So the fact that it comes in this specific shape is lost in this point of view. I don't know it now officially. I'm just looking at this specific situation. I solved my homogeneous equation. I found one solution and used it to find all solutions. Now, this brings me back to this general theory of linear equations. When you have linear equations and they are homogeneous, then the solutions form a linear space of a certain dimension. Here, the dimension is 1. This is one vector of the basis, and these are all linear combinations. So this is the span of the basis. It sort of fits like that with the general theory from linear algebra. So I have a homogeneous solution, as I call it. And in step 2, I decide to do variation. And I'm looking for a solution in the form cx ux. Let's see. I substitute my gas into the given equation. And I get the derivative here, which is c prime x ux plus cx u prime x. And then I have to put plus ax and my gas, the function y, cx ux. And that's it. Then there is the equality sign. This should be equal to bx. So far, so good. Now, let's have a look. C prime x ux plus, and I can factor out cx out of here. What do I see? I see u prime plus ax ux. And this is supposed to be bx. Now, what are the assumptions now? My assumption was, and that's the single assumption, that ux solves the associated homogeneous equation. Well, that's exactly the left-hand side of associated homogeneous equation when I compare it with my equation there. So this must be 0, and that's the cancelling. So it is not based on the fact that we have the exponential here. The real cause for the cancelling is the fact that we are working with the solution to the associated homogeneous equation. And we get c prime x ux is equal to bx. So we can see the general pattern. We take our gas, we differentiate c, and we make it equal to the right-hand side of our equation. So this is really the equation. If you want to remember something, that this is the thing to remember. How to pass from your gas to your equation. It will save you some work. But then you have to, well, it will occupy an extra place in your memory. So it's a question whether it's worth it. It's up to you. Okay, here we go. Now we are ready for the algorithm. So we are given an equation which is of a linear equation of order 1. And we use separation, or perhaps some other tricks, if we know them, if we can use them in a specific situation, to find a general solution, which we express as c times ux. Now you can see where this comes from. So that's the general form, this one. And then again, you have a choice. You can either remember it, or you simply do this substituting and cancelling procedure. And you get your equation c prime ux is equal to bx. You integrate, and then everything comes exactly the way that we saw it here. And you have a choice. Either you use the form with plus c in this integral, and you get a general solution right away, or you do it without plus c, you get a particular solution, and then you add the homogeneous solution to it. I talked about it before. So that's the general procedure, the way I want to see it, so that I can generalize it later in about a few weeks. And that's it concerning the variation. If you still have some time, you can stick around and I will do one more example. We saw this example before. We solved it by separation, and it wasn't bad. It was actually just a few lines. So that's a nice problem for separation. But this time we will try it differently. I'm going to multiply out this bracket and rearrange it a little bit. And we see that this can be also considered a linear differential equation. This part is the coefficient ax. This part is the right-hand side bx. Now, some students actually like to memorize the formulas from this theorem, and then they just substitute a and b into those formulas, they work it out. And actually, yeah, this can be done. But I do not exactly recommend doing it that way, because memory is faulty. And when you're memorizing formulas like that, it's very simple to make a little mistake, for instance, in the sign. Is it e to negative ax or positive? You know, if you make a tiny little mistake in the formula, then the answer is simply wrong. So, at least from my point of view, it's much safer to simply remember the basic idea, because ideas are easier to remember and they are not so detailed. So, here's the idea. Let's follow the algorithm. First, we will solve the associated homogeneous equation. So I put 0 here, and just for convenience, I will move this term again to the right. Now I can see it better. Now we apply the usual separation. So I see this as dy over dx, rearrange things a little bit. And after I do it, I get the following equality. And of course, this is true only assuming that y is not 0. We should be careful. We integrate. And by the way, I kept 2 on the right because usually when you see a constant in those problems, then actually it's the sign that the author of the problem was nice to you and wanted to make things nicer in the end. So it's a good idea to leave constants when you see them like that. Okay, this is logarithm of y, and integral of 2x is x squared. Yeah, you see it? 2 is nice here. And now we solve it the usual way for y. And experienced solvers would perhaps jump directly to the solution, because this appears so often that, well, perhaps you might even memorize it. Although I do not quite recommend it. Anyway, this includes for d is equal to 0, the stationary solution. And of course, we shouldn't forget writing the region of existence. It's actually not so crucial here because this is just a preparatory step, but I'm getting myself into the habit of writing it automatically, and then on the test I do not forget. Okay, is there any restriction? Not here, not here, not here. X is real. So that's the first step. I solved the homogeneous equation. Step 2, variation. I am looking now for a solution of the form dx e to x squared. And I will try the structural approach because I didn't do it before, officially at least, in that previous example. So I'm looking for a particular solution of this form. And now I have a choice. Actually, I do remember the equation which I get out of it. I should get the following equation. D prime x e to x squared is equal to negative 2x. Because this is so simple, the principle is so simple that somehow it sticks in my memory, even without trying. But let's see whether it works out. I take dx e to x squared, and I substitute it into my equation. So I differentiate d prime x e to x squared plus dx e to x squared times 2x, that's the derivative, minus 2x dx e to x squared, that's for y, and this should be negative 2x. Cancelling, do I see it? Yes. If you do not see cancelling, then most likely you made some mistake in calculations. That's first possibility, in particular here perhaps. And the second possibility is that your equation is not linear. Because without linearity, we don't have cancelling. Unless you are extremely lucky, wouldn't count on it. So this really only applies to linear equations. Yeah, after cancelling, we get exactly this. So d prime x is negative 2x e to negative x squared. And now we integrate. Dx is equal to integral negative 2x e to negative x squared dx. And now we look at it, and we can see a composed function here, which usually is an invitation to substitution. Now, will it work? The inside function is here. If I take derivative, I get minus 2x. And by extremely lucky coincidence, I can see it also here. So substitution u is equal to negative x squared will really work. This part will become du, and we get e to u here. And we work it out in the usual way. You know your calculus. No problem there. And it becomes e to negative x squared. And I'm not writing plus c, and I'm not feeling guilty about it. I have a special parameter not to do that. Okay, this is my dx. I substitute into my gas here, and I get particular solution. My particular solution is e to negative x squared multiplied by e to x squared, which is just 1, surprisingly enough. And therefore, the general solution by the structural theorem from linear theory, general solution is the particular solution plus the homogeneous solution, which is over here. And x belongs to real numbers, because no new restriction came around. Yeah, this is all working for real numbers. And that's exactly the solution which a while ago we obtained by separation when we applied it like that. So that's a match. It shows that the variation again did a good job for us. Now, when you look at the previous lecture where we did it by separation and compare it, you will see that this is about twice as much work. So really, if I can use separation, I definitely prefer it. But variation is also nice. And that's it for today. See you.